All right, let's dive into this explainer with a concept that might literally bend your understanding of physics. We're going to explore a phenomenon that honestly sounds like pure science fiction, looks like Hollywood special effects, but is actually one of the most vital tools we have in modern astrophysics and nuclear science. We are, of course, talking about Cherenkov radiation. So, is it actually possible to travel faster than the speed of light? I know. It sounds like the ultimate trick question. We've all had it drilled into our heads since middle school that Einstein's universal speed limit is entirely unbreakable. At roughly 300,000 kilometers per second, absolutely nothing in the universe is supposed to outpace light. But, as with all great scientific mysteries, the answer isn't a simple no. Because the truth is, yes, as long as you're in the right medium. See, the crucial thing to remember here is that while absolutely nothing beats light in a perfect vacuum, light actually hits the brakes when it moves through transparent mediums like water or glass. And because light slows down, it suddenly creates this massive loophole, a local speed limit that other highly energetic particles can actually break. Which brings us to part one, the mysterious blue glow. Let's start grounded, right here on Earth, looking at one of the absolute most mesmerizing sights in modern science. If you've ever looked at photos of an active nuclear reactor, you've probably noticed this intense, ethereal blue light glowing around the submerged fuel rods. First observed by Russian physicist Pavel Cherenkov back in 1934, this is not just some neat visual trick or a reflection, it's a literal shockwave of light happening right inside those reactor pools, and it's caused by subatomic particles tearing through the water faster than the light around them. Now, you might be wondering, why is it always blue? Well, what's truly fascinating is how this differs from standard thermal glow or fluorescence. When a charged particle rips through water, it violently excites the molecules around it. As those molecules settle back to normal, they release energy as photons. But this emission doesn't have specific spectral peaks. It's a continuous spectrum where the intensity just shoots up as the wavelength shrinks. That means most of this energy is actually blasting out in the invisible ultraviolet range. But because human eyes are super sensitive to green and blue, the edge of that intense spectrum bleeds into our visible range, and our brains perceive it as a brilliant, brilliant blue. Moving on to part two, breaking the speed limit. To truly understand how particles pull this off, we just need to look at the math of the medium. Let's just think about the numbers for water. Because water has a refractive index of 1.33, light is forced to slow down to about 75% of its vacuum speed, or 0.75 C. Now, inside a nuclear reactor, fission is producing highly energetic electrons that are shooting out at speeds much closer to 100% of C. Because the electron is moving faster than 0.75 C, it just completely outpaces the light traveling in that exact same water. So what's physically happening? When a charged particle blasts through a medium faster than the local phase velocity of light, it totally disrupts the electromagnetic field, polarizing the molecules right in its path. Normally, if a particle is moving slowly, the light waves emitted by these disturbed molecules just ripple away gently, kind of like a pebble dropped in a pond. But when the particle is moving faster than light can travel in that space, the molecules simply don't have time to recover. The emitted waves bunch up and constructively interfere with one another. It's exactly like a supersonic jet breaking the sound barrier. You know how a jet traveling faster than sound forces its own sound waves to overlap, creating that massive conical shockwave we hear as a sonic boom? Well, Cherenkov radiation is the exact same physics, just applied to light. An electron is breaking the light barrier in that specific medium, creating a luminous conical shockwave of photons. It is literally, in every sense, a sonic boom of light. Okay, part three, flashes in the dark. Let's scale things down from giant reactors to the biology of the human body in low Earth orbit. During the early Apollo missions, astronauts reported something incredibly eerie. Even when they were trying to sleep in complete darkness, with their eyes tightly closed, they would suddenly see strange visual flashes, streaks, and little points of blue-violet light. This bizarre phenomenon, known as astronaut phosphenes, totally puzzled scientists for years. I mean, how do you see a flash of light in a pitch-black spacecraft with your eyelids shut? The answer is absolutely wild. These astronauts were basically acting as tiny walking particle detectors. The vitreous humor, that's the clear fluid inside your eyeball, has a refractive index of about 1.34. That drops the local speed of light to 75% of its maximum. Out in deep space, without the Earth's thick atmosphere to shield them, highly relativistic cosmic rays would occasionally shoot straight through an astronaut's eye. Moving faster than the local speed of light in that eye fluid, the cosmic ray would generate a microscopic Cherenkov cone that projected directly onto the retina. It literally triggered the visual sensation of a streak of light from inside the eye. Which leads us beautifully into part 4, Earth as a giant lens. Because if the fluid in a single human eyeball can act as a particle detector, just imagine what we can do using our entire planet. To measure incredibly elusive things like high-energy astrophysical gamma rays and neutrinos, astronomers use massive observatories like HESS, MAGIC, Veritas, and IceCube. But here's the catch. The flux of these cosmic particles is so incredibly low that a standard satellite detector in space, which is maybe a square meter in size, just isn't anywhere near big enough to catch them. So, astronomers rely on the Earth itself as an intrinsic part of the detection technique, basically turning the planet into a massive telescope lens. Here is how this atmospheric technique actually works. Because primary cosmic rays and gamma rays get absorbed high up in the atmosphere, we can't easily detect them on the ground. Instead, we wait for a high-energy particle to slam into the upper atmosphere. This triggers a massive cascade of secondary charged particles, an air shower, peaking at about 10 kilometers up. These secondary particles are traveling faster than the speed of light in air. As they fall, they emit Cherenkov light, which beams forward and creates a massive pool of faint blue light on the ground, roughly 130 meters across. Arrays of highly specialized mirrors on the ground capture this nanosecond-long flash, allowing us to trace it all the way back to its cosmic source. And get this, it doesn't just work in the sky, it works deep underground too. Take the IceCube Observatory in Antarctica. Neutrinos are famously elusive ghost particles that rarely interact with matter. But every once in a while, one crashes into an ice molecule deep underground, creating a charged lepton like a muon. That muon tears through the pristine Antarctic ice faster than the speed of light in ice, emitting a Cherenkov bow shock. So whether we're looking up into the thin air or deep down into a cubic kilometer of solid ice, we're using the exact same sonic boom of light principle to catch these elusive particles. Part 5. Unlocking the deep cosmos. So, what is all this eerie blue light actually helping us see out there in the universe? Cherenkov radiation acts as a messenger from the deepest, darkest parts of the cosmos. It lets us observe the universe's most violent, extreme engines. We're talking about the fiery aftermath of exploding stars, the intensely magnetic environments around rapidly rotating pulsars, and the terrifying accretion disks of supermassive black holes at the centers of active galaxies. These environments generate particle energies that completely dwarf anything we can create in human-made colliders on Earth. They reveal an entirely invisible, high-energy universe we could never, ever see with standard optical light alone. And the future of this field is moving fast. Right now, ground-based arrays are doing the heavy lifting, mapping out the high-energy universe. But future missions like GEM-USO and POMA will literally take our Cherenkov detectors off the ground. By putting them in suborbital balloons or even looking down at the Earth's atmosphere from space, we can capture even rarer, ultra-high-energy cosmic events, unlocking even deeper mysteries of the cosmos. But wait, I know what you're thinking. We established earlier that this phenomenon strictly requires a medium, like water, glass, or air. We literally said it cannot happen in a perfect vacuum because nothing is faster than the speed of light in a vacuum, right? Well, physics is crazy, and the universe has one final mind-bending trick up its sleeve. Enter quantum vacuum polarization. Around incredibly dense, highly magnetic objects like pulsars and magnetitars, the sheer magnetic force is so overwhelmingly powerful that it actually polarizes the quantum vacuum of empty space itself. It perfectly aligns these virtual electron-positron pairs that constantly pop in and out of existence. This bizarre quantum effect essentially gives literally empty space an effective refractive index that is actually greater than 1. Because this extreme magnetic polarization forces the vacuum itself to act like a physical medium, light actually slows down just a tiny, tiny fraction. And that means highly relativistic particles emitted by the pulsar can theoretically travel faster than light in that specific region. They emit Cherenkov radiation, known as CRQV, in what is essentially empty space. We are literally using the rules of medium-based physics to break the rules of a vacuum. It really leaves you wondering, doesn't it? We started with what we thought was an unbreakable universal speed limit, found a loophole in a pool of water, used that loophole to turn our entire planet into a giant telescope, and finally watched a magnetic field turn empty space into a medium. If the faint blue flashes of Cherenkov radiation can reveal all of this, what other unbreakable rules of the universe are out there, just waiting for us to find the right loophole?